Section 1.2 Inverse Functions. In the last example from the previous section, we looked at the two functions f of x, which is equal to 3x minus 2, and g of x equals x over 3 plus 2 over 3, and saw that f composite g of x was equal to g composite f of x, which would equal x. And as noted in that section, this means that there is a nice relationship between these two functions. So let's just see what that relationship is. Now, considering the following evaluations. For the function of f, we're going to plug in -1 in for the function f. So we put in -1 into the function. 3 times -1 minus 2 gives us -5. Then what we're going to do is we're going to take that -5 and plug it into the function g. So we get -5 over 3 plus 2 over 3, which is equal to -3 over 3, which gives us -1. Now, if we start with g and then put 2, let's put in 2 into the function. So we have 2/3 plus 2/3, which is equal to 4/3. And now we're going to put 4/3 into the function of f. So it's going to be 3 times 4/3 minus 2, which becomes 4 minus 2, which is 2. So what do you notice? When we plug in -1, and we end up getting -1 out. We plug in 2, we got 2. Now, in the first case, we plugged x equals -1 into the function f of x and got the value of -5. We then turned around and plugged x equals -5 into g of x and got a value of -1, the number that we started off with. In the second case, we did something similar. Here, we plugged in x equals 2 into g of x and got a value of 4/3. We turned around and plugged this into f of x and got a value of 2, which is again the number that we started with. Note that we really are doing some function composition here. The first case is really g composite f of -1, which means we're finding g of f of -1, and f of -1 turned into -5, and then -5 into the function g gave us -1. And the second case was also f composite g of 2, which was f of g of 2. We plugged in the value of 2 into the function of g, and we got 4/3. And then plugged 4/3 into the function of f, and then we got 2. Now, note as well that these both agree with the formula for the compositions that we found in the previous section. We get back out of the function evaluation the number that we originally plugged into the composition. So, just what was going on here. In some way, we think of these two functions as undoing what the other did to a number. In the first case, we plugged x equals -1 into f of x, and then plugged the result from this function back into g of x, and in some way, g of x undid what f of x had done to x equals -1, and gave us back the original x that we started with. Function pairs that exhibit this behavior are called inverse functions. Before formally defining inverse functions and the notation that we're going to use for them, we need to get a definition out of the way. A function is called one-to-one if no two values of x produce the same y. Mathematically, this is the same as saying f of x1 does not equal f of x2 whenever x1 does not equal x2. So a function is one-to-one if whenever we plug different values into the function, we get different function values. Sometimes it is easier to understand this definition if we see a function that isn't one-to-one. Let's take a look at a function that isn't one-to-one. The function f of x equals x squared is not one-to-one because both f of -2 equals 4 and f of 2 equals 4. In other words, there are two different x values that produce the same value of y. Note that we can turn f of x equals x squared into a one-to-one function if we restrict ourselves to where x is in between 0 and infinity, and then we're including 0. This can sometimes be done with functions. Now, showing that a function is one-to-one is often tedious and or difficult. For the most part, we are going to assume that the functions that we're going to be dealing with in this course are either one-to-one or we have restricted the domain of the function to get it to be a one-to-one function. Now, let's formally define just what inverse functions are. Given two one-to-one functions, f of x and g of x if f composite g of x is equal to x and g composite f of x is equal to x. Then we say that f of x and g of x are inverses of each other. More specifically, we will say that g of x is the inverse of f of x and denote it by g of x, which is equal to f inverse of x. Likewise, we could also say that f of x is the inverse of g of x and denote it by f of x, which is equal to g inverse of x. Now, the notation that we use usually depends upon the problem, and in most cases, either is acceptable. And remember, this -1 represents inverse, not an exponent of -1. Now, for the two functions that we started off this section with, we could write either of the following two sets of notations. We can say that f of x is equal to 3x minus 2, and then f inverse is equal to x over 3 plus 2 over 3. Or we can write g of x is equal to x over 3 plus 2/3, whereas g inverse of x is equal to 3x minus 2. Now again, be careful with the notation for inverses. The -1 is not an exponent, despite the fact that it sure does look like one. When dealing with inverse functions, we've got to remember that f inverse of x does not equal 1 over f of x. Now, this is one of the more common mistakes that students make when first studying inverse functions. The process for finding the inverse of a function is fairly simple, although there are a couple of steps that can on occasion be somewhat messy. So here is the process. Finding the inverse of a function. Given the function f of x, we want to find the inverse function f inverse of x. Step 1, we first replace f of x with y. This is done to make the rest of the process easier. Step number 2, we replace every x with a y and replace every y with an x. Number 3, solve the equation from step 2 for y. This is the step where mistakes are most often made, so be careful with this step. Number 4, replace y with f inverse of x. In other words, we've managed to find the inverse at this point. And then number 5, verify your work by checking f composite f inverse of x is equal to x and f inverse of f of x is equal to x are both true. This work can sometimes be messy, making it easy to make mistakes, so again, be careful. Now, that's the process. Most of the steps are not all that bad, but as mentioned in the process, there are a couple of steps that we really need to be careful with, since it is easy to make mistakes in those steps. In the verification step, we technically really do need to check both f composite f inverse of x is equal to x and f inverse composite of f of x is equal to x are true. Now, for all the functions that we're going to be looking at in this course, if one is true, then the other will also be true. However, there are functions, they are beyond the scope of this course, however, for which it is possible for only one of these to be true. This is brought up because in all problems here, we will be just checking one of them. We just need to always remember that technically we should check both. So let's work on some examples. So, given f of x, which is equal to 3x minus 2, we want to find the inverse of x. Now, we already know what the inverse to this function is, as we've already done some work with it. However, it would be nice to actually start with this since we know what we should get. This will work as a nice verification of the process. So let's get started. We'll first replace f of x with y. So therefore, we're going to get y, which is equal to 3x minus 2. Next, we're going to replace all the x's with y and all the y's with x. So now we have x, which is equal to 3y minus 2. And now we're going to solve for y. So now we have x plus 2 equals 3y. We divide both sides by 3, which is 1/3 times x plus 2, and we get y, which is equal to x over 3 plus 2 over 3. Finally, we're going to replace y with f inverse of x. So f inverse of x is equal to x over 3 plus 2 over 3. Now, we need to verify the results. We already took care of this in a previous section. However, we really should follow the process, so we'll do that here. It doesn't matter which of the two that we check, we just need to check one of them. This time, we'll check f composite f inverse of x is equal to x is true. So f composite f inverse of x, that means this is going to become f of inverse of x, and we found f inverse of x to be x over 3 plus 2 over 3. And then we're going to plug that into the function of f. So we get 3 over x over 3 plus 3 times 2 over 3 minus 2, which gave us x plus 2 minus 2, which gave us x. Next example. Given g of x, which is equal to the square root of x minus 3, we want to find g inverse of x. Now, the fact that we're using g of x instead of f of x doesn't change how the process works. Here are the first few steps. So we have y, which is equal to square root of x minus 3, and then we're going to replace x and y to be x, which is equal to the square root of y minus 3. And now we need to solve for y. We will need to first square both sides and then proceed as normal. So we're going to square both sides to get rid of the radical. So we have x squared, which is equal to y minus 3. And then solving for y, we add 3 to both sides. So y is going to equal x squared plus 3. So this inverse is then g inverse of x is equal to x squared plus 3. Finally, let's verify, and this time we'll use the other one just so we can say that we've gotten both down somewhere in an example. So g inverse composite g of x, which is equal to g inverse of g of x. So g of x is the square root of x minus 3, and we plug that into the inverse function, which is the square root of x minus 3 squared plus 3. When we square the square root, we end up with x minus 3 plus 3, and we get x. So we did the work correctly, and we do indeed have the inverse. Now, the next example can be a little messy, so be careful with the work here. Example 3. Given h of x is equal to x plus 4 over 2x minus 5, find h inverse of x. Now the first couple of steps are pretty much the same as the previous example, so here they are. We're going to replace, interchange x and y, so it becomes now y equals x plus 4 over 2x minus 5, becomes x, which is equal to y plus 4 over 2y minus 5. Now be careful with the solution step. With this kind of problem, it is very easy to make a mistake here. So what we're going to do is we need to solve for y. So in order to solve for y, we're going to multiply both sides by 2y minus 5. Now we have a y on both sides of the equation, so we need to distribute the x first. So we get 2xy minus 5x, which is equal to y plus 4. And now what we want to do is we're going to combine all the y variable terms on the left side and all the other terms on the right side. So we have 2xy minus y, which is equal to 4 plus 5x. And what that allows us to do is to be able to factor out the y, and then we can divide by 2x minus 1. So y is equal to 4 plus 5x over 2x minus 1. So if we've done all our work correctly, then the inverse should be h inverse of x, which is equal to 4 plus 5x over 2x minus 1. Finally, we'll need to do the verification. This is also a fairly messy process, and it doesn't really matter which one we work with. So composite h inverse of x. So we have h of h inverse of x. We know that h inverse of x is 4 plus 5x over 2x minus 1. And then we're going to plug this value in for x into the value of h, into the function of h. So we have 4 plus 5x over 2x minus 1 plus 4 divided by 2 times 4 plus 5x over 2x minus 1 minus 5. Now, okay, this does look messy, but let's simplify things up a little bit by multiplying the numerator and denominator by 2x minus 1. Because 2x minus 1 is in the denominator of this fraction here, and 2x minus 1 is in the denominator of this fraction here in the denominator. So if we multiply both by 2x minus 1, that means that we can eliminate the 2x minus 1s. So we have 2x minus 1 times 4 plus 5x over 2x minus 1 plus 4. 2x minus 1 times 2 times 4 plus 5x over 2x minus 1 minus 5. So now what happens here? Well, we eliminate the 2x minus 1 here, and then we have to multiply 4 times 2x minus 1 which gives us this numerator here. And then likewise, we eliminate that one, and then this becomes 5 times 2x minus 1, which gives us this here. And so now we're going to distribute the 4 and the negative 5 to get 4 plus 5x plus 8x minus 4. Here we get 8 plus 10x minus 10x plus 5. Combining like terms, we get 13x over 13, which is equal to x. So wow, yeah, that was a lot of work, but it all worked out in the end. We did all of our work correctly, and we do in fact have the inverse. Now there is one final topic that we need to address quickly before we leave this section. There is an interesting relationship between the graph of a function and the graph of its inverse. So here's the graph of the function and inverse from the first two examples. So if we take a look at the first example, here's the graph of f inverse of x and f of x. And then we have a dotted line which represents y equals x. Over here we have g inverse of x and g of x. Now in both cases we can see that the graph of the inverse is a reflection of the actual function about the line y equals x. This will always be the case with graphs of a function and its inverse.